Assalamualaikum warahmatullahi wabarakatuh. My name is Jaabar. The number of AE 6. So this is our circuit. So now I will explain and I will perform the presentations on the flow of the circuits, the overall circuits. So it starts with the reference, speed reference in RPM here, and then it will go through into the VIP. Then it will flow into the speed controller, and then go into the PWM. But however here, PWM in duty cycles, units, and also value. And because of that, it cannot go through into the duty cycles. In this case, we need to convert the speed reference into the PWM, into the duty cycle. So that will be covered later. And then after we convert it, it will send a signals or even pass. You will send a signal to turn on and or either off state into the switching device here, which is MOSFET, that connected with the overall buck circuit. So in this buck converter, the switching device MOSFET will be activated, and then the voltage source will be supplied the whole circuit, and then it will produce the output voltage. With the output voltage, it will supply the DC motor that arranged right here. Then the DC motor will make a movement, and then it will record a speed at the last that we need to observe after that. That's all. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hashim Mu'min bin Muhammad Noor with which number of AE1800076. So today I will show you the video presentation of our system, but for my part, which is I will explain to you about the relation between the pulse width modulation, or we used to call it as PWM, and the buck converter, right? So first of all, as we know, pulse width modulation is a fancy term of describing any type of digital signal, and it is also used in a wide variety of applications. And in DC motor speed controlling circuit, PWM varies the motor speed by controlling or simulating by reduction or increasing in supply voltage, right? So today I will show you the relation between the PWM and the buck converter, right? So theoretically, the buck converter, as we know, the voltage output will be low than the voltage input, since it will be decreased, right? So first I'll try to calibrate this circuit by using the reference speed as a 1715 RPM. So we can run it. Theoretically, the voltage output will be low than the 270, but for 170 RPM, 1750 RPM actually will be same, since 1750 RPM is actually equal to duty cycle with 1, right? So the output will be 140, right? As you can see here, 140, and the duty cycle is here is 1. Okay, that's for the with duty cycle 1. So other than that, we can obtain by using other value such as 875 RPM actually. Why? Because it is equal to 0.5 duty cycle. So technically, the voltage output of the buck converter will obtain voltage around 118, 120, right? So we try to determine it whether it's correct or not. Right, 1 at 175, so the duty cycle here should be 0.5 and the voltage output here should be 120 something. Right, so we proceed whether it's follow the theoretical or not. So alright, so duty cycle is 0.47, also equal to approximately to 0.5. Alright, then the voltage output here of the buck converter is 118.7, so it is actually approximate with theoretical value, which is 120 volt. So this system is actually correct since the voltage of the buck converter output is below than the voltage input. So that's all for my part. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azam bin Shaidi. My magic number is AE180037. Today I would like to present the component function and troubleshooting. The first one, we have separate excited DC motor. This motor convert electrical energy into mechanical energy. The preset model for this motor is we have 5 horsepower. The input voltage is 240 volt and 1750 rotation per minute, and the field voltage is 150 volt. Okay, now we have PWM. PWM operate like a switch. The switching frequency that has been chosen is 50 kHz. This value will determine the inductive and capacitive load in the buck converter. When we set up the switching frequency to 50 kHz, the RLC load must be in lower value because we want to make sure the system are light and low cost. Next, we have capacitive load. The capacitive load function to store the electrical charge, and then we have inductive load. The inductive load is to store the energy in the magnetic field when the electrical current flow through it. And then we have PID controller. And then we have DC voltage source that's supplying a voltage into the system. And then we have MOSFET. MOSFET is a semiconductor device that widely used for switching purpose. Okay, for the troubleshoot, the problem is the parameter speed flow through the PWM must be converted into the duty cycle due to different value and unit. So the solution is conversion that include applying the mathematical approaches into the magnet system design. Okay, we have equation 1, equation 2, and equation 3. And then by substitute the equation 3 into the equation 2, we have the power equal to I naught multiplied by the duty cycle and multiplied to the V input. Then the substitute the power equation into the equation 1, and we have the duty cycle formula. Therefore, since we want to observe the relationship between duty cycle and the speed, and we substitute the duty cycle that has been calculated into the duty cycle equal to gain times by the speed, and we rearrange the equation, get the gain as the title of the formula, and we have gain equal to torque over 30 over pi times by I naught times by the V input. This is the plot representation for this system. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad bin Kamaruddin. My metric number is AE180068, and now I'm going to present about the results part, and I'm going to talk more specifically about the graph. So let's start. So as you can see here, this is our first graph. For graph 438 RPM input. So the purpose of this graph is to see the time needed to achieve the time needed for motor to achieve the constant speed. So in this graph, you can see that it have two part. The first part is where it going is unstable, which is going up from zero, is going up and then going down. This normally at the beginning of the graph. And then the second part is the constant speed, where you can see the constant line here. So the first part that going up and down is called the time relay, and the second part is calling the constant speed. So technically, the shorter the time relay, the better the system it is. So the purpose of this graph, like I said before, is to see the time needed to achieve the constant speed. So in this graph, you can see the x-axis is the time, and the y-axis is the motor speed in radian per second. So from radian per second to change to RPM, we only need to multiply by 30 over pi to get the RPM value. But we don't have to calculate because it already shown the RPM value in MATLAB simulation. So we only want to see what the time for achieve the constant speed. So for this first graph, which is the input is 438 RPM, we can see that it achieved the constant speed at the time of 0.234 second. So if we're looking at the second graph with the input is 875 RPM, we can see that the time to achieve the constant speed was 0.245 second. It's around here. And for the last graph, for input 1750 RPM, the time to achieve the constant speed was 0.253 second. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Azlin binti Niklin with metric number AE180012. So I'm going to talk about the result and discussion. So first of all, after we setting up all of the components for the circuit, we need to set up our torque load. So in order to set up the torque load, we need to calculate it first. So we need to use our power, which is 5 horsepower. We need to change it into kilowatt. And then our motor speed, which is 1750 RPM, we need to change it into radian per second. Then after that, we can calculate our torque load using this formula, which is we can get our torque load 20.35 Newton meter. Our torque load need to be fixed for the whole process. That's why we use our maximum value of motor speed, which is 1750. Because we can, if we use the maximum value of motor speed, we can estimate the other values to use in this task. Because for this task, we need to use 3 different values for the speed motor. And after that, I'm going to talk about the reading of the motor speed, the result that we get from the motor speed, and the result for duty cycle. So first of all, we use these 3 values to insert in the circuit, and then we get the output like this. Supposedly the output need to be same just like the input, but then we get a little bit different from the input, and after that I can calculate the percentage error of the motor speed. And same goes to the duty cycle. We need to the duty cycle, which is the output of duty cycle, need to be to be same as the actual duty cycle, but then because of maybe some errors that occur during the whole process, this duty cycle didn't get like exactly like the actual duty cycle, then I can calculate the percentage error for the duty cycle also. So for the result, we put the percentage error for both motor speed and the duty cycle for the whole process. That's all from me. Thank you.